Oh, welcome back, and I'm trying to redo this video, and I will test the sound and see if this is actually clear or not. So let me try this. Okay, it seems to be working. The sound is okay. So in this part, we are discussing radiant floor heating, and radiant floor heating is the only or the most common way to use radiation as the mode of heat transfer instead of convection. So when we did baseball radiators, even though they're called radiators, they use convection as the main heat transfer mode. With radiation, we do use radiation. So for radiant floor heating, we're using radiation. And this scary equation here, you don't have to worry too much about it, but it is very similar to what we used to have before. Remember before, I'm going to use my camera now and increase the camera size so we can look at that. And if you look here, we used to use Q equal area times U times delta T. This you know, right? This one is for radiation. We don't have to go too deep into it. And it does say Boltzmann constant, actually it's sigma times alpha times T hot to the fourth, T cold to the fourth times area is the heat transfer through radiation. So what you need to look at is those two are constant. This one called the emissivity constant is between 0 and 1, and this is based on the material. So this is a constant number, and that's the emissivity. And I think it's no, epsilon is the emissivity, and this is the Boltzmann constant, which is the person who put this equation. And the T hot and T cold are temperature of the hot object and the cold object to the power of fourth difference between them, and finally is the area. If you look at the book, there's a there is here some kind of elaboration of how this works. And I don't want to scare you with this. We're not going to use it. But what I'm trying to convey to you is if you look at the heat transfer through radiation, these things are constant. We cannot change much of them. And there's the temperature of the object, the temperature of the water are something we can change, and also the area. So the area is a very important factor when it comes to radiation. How much surface area do we have to radiate from one object to another? So probably if you notice, if you go to a restaurant and they have those radiator heaters, they come in a kind of like a dish format, so it can spread out more radiation. And you need the big surface area to use radiation, even though the temperature is not going to be that hot. So let's think about that a little bit for our purposes. I don't want to again scare you too much or get too much science into it. So if you look at in the book in chapter 6, page uh, 86, you'll see some examples about radiation and how does it function, some of the limitation, and how do we do some of those calculation in here. And if you look at the end of the book, the formula page at page 159, looking at that, if you look at radiator selection and you look at radiant floor heating, you see some equations here. And these equations are just a manipulation of the major equation that I used in the beginning, which is radiant heating load Q equal radiation rate times the area times degree difference. So going back to our sheet here to kind of have some kind of similarities. So we had Q before. I'm gonna go back and make this a little bit bigger. We have Q equal area times U times delta T. That's what we know for heat transfer through conduction through an object. So Q radiation will be something very similar, something called the radiation rate, which is corresponds to the U uh, times area times delta T. So you see these things are kind of still the same, the area and delta T, and the U became the radiation rate. This kind of makes things a little bit much easier. Okay, there's that's so you don't have to look at this again. We'll move on and let's see what else is there. So advantages of having radiant floor heating. So radiant floor heating is the best you can do for a place that has that you want to invest some money in it, and you want to have the proper amount of heat distribution. So it's very comfortable temperature profile to the human body. What does that mean? It means that the human this is the if if I have in here, look at the small little camera, and this is the person in here, you will have that temperature at the bottom is going to be around 85 and around face level is around 65. So that's a really good temperature profile where you have hot temperature. If you have this axis here for temperature profile, this is hot temperature and this is low temperature as we go up. So the temperature profile will give you heat around the feet and cooler air around the eyes. So it's very, very comfortable. So those who use radiant floor heating usually enjoy and love this kind of advantage. It has the perfect match for each heated zone. So with radiant floor heating, we'll have a panel, and this panel will have all the hot water available, and each room will have its own zone and its own hot water coming from the manifold and supplying that room with heat. So you can change the heat requirement for each room based on that zone. And there's a schematic here in the book that actually illustrate that. I'm going to go back to page 86. I don't know if I put it in here. I think it was in the other chapter. I had a picture that shows radiant floor heating. I think it's in the appliances here. It is somewhere in here. But the point I'm trying to make is that when you have, let's look at this. If you have this is your floor plan, and you have different rooms. Each room can have its own loop of radiant pipes, and you can control the temperature goes through that loop based on the hot water you supply to this room. And the other advantage here is that radiant floor heating systems operates at lower temperature. So 85 to 95. That's much lower than hot water system with the baseboard radiators where you have to have the water heated to 180, or steam system where you have the water evaporated into steam. So that's very, very low, and it's very convenient. So you can use other sources for heat instead of gas or oil burners. The air in the room is stratified. That means all the air the same temperature, not hot region or cold region. So it's kind of uniform temperature throughout the room. There is no visible heating units. You're heating the floor or the walls, so you don't see the heaters or appliances. You just feel comfortable inside the room. There is no air coming to your pump being pumped or towards you. There is no, you don't hear any crackling or anything. And if the system is designed correctly, you don't even hear the water running through the floor. It's very quiet. There is no noise coming from the system. It does not stir up the air. It's very versatile. It can be coupled with other things and different kind of heat source like solar panels or geothermals, because it does operate at lower temperature. Very comfortable and it says very comfortable bare floor temperature, so you can walk on this floor barefooted. So people usually prefer that for bathrooms and kitchens. Okay, some of the limitations with this system is that it has very slow reaction time. The system takes a relatively long time to reach desired temperature. It is the kind of system that you want to leave on for the entire season. So if you turn it on, probably it's going to take a while to heat up. So that's one of the drawbacks of that system. The furniture can cause a problem if you have a room with big furniture or a lot of carpet, or it might slow down the system reaction and might hinder the progress of it. So that's something it has to be incorporated into the design from the beginning. Like let's say it's a big hall and it was designed to have a lot of floor area, and suddenly you're going to put a big table or conference table in there. That's something you have to be put into consideration as well. Again, it does not filter the air, and that's not the main purpose of a heating system, right? Leaks can be very problematic. I know a lot of houses been designed to have radiant floor heating, but then there was a leak and the whole system got mothballed, and it has to be changed. It has to be changed to something else, because this is not going to be uh, uh, easily or cheaply repaired. Okay, building material has to be tolerant to the heat. I mean, if you have carpet or padding that cannot tolerate a temperature between 95, that should be coordinated with the building people. Okay, system specification. The radiant system specification are as follows. You have a header as a manifold, and so again, you have a hot water system supply in here that supply to all those rooms, and the incoming water will go back and unified into a manifold. Uh, each room has its own zone and its own loop. The heat supply to each zone depends on many things: the tube size, tube length, and tube spacing, and these little aspects that I'm going to talk about right now. So if we think of if this is a room, and I'm trying to heat this room using radiant floor heating. Again, look, think of the equation, okay? Radiation rate times area times delta T. Let's say we fixated the area we cannot change, and the temperature inside we cannot change, so we only can change the temperature of the water going into those tubes, right? What goes into the calculation of the radiation rate? So chances are you're going to buy preset radiation rate for that floor heating. But just so you know how this radiation rate is calculated, it's based on the tube size. So that's the diameter of the tube, because again, this is going to be the interaction area between the tube and the floor. It is the surface area of the tube. So the size of the tube does matter. Tube length, because again, this area over here will equal the circumference of the circle, which is 2 pi r times the length. So this circumference times the length. So the length of the pipe does matter. The size of the pipe does matter. The tube spacing, this is the spacing between them, does matter, because again, you will have less dispense of heat and more dispense of heat based on that spacing. The filling, what are you gonna fill that with? Gravel, cement, air. That makes a difference in how much heat you have in that floor. And what else? So these are all those things goes into the radiation rate, and I have an example of how this is calculated. Again, just for information, I don't think I'm going to incorporate these calculations in any quiz and so on. So again, the system has to be pressure tested after it's done, and the installation has to be coordinated with construction contractor before you put it in, because you don't want to install that then somebody comes in and put some holes or put some carpet and puncture your system. And even before you run water into the system and commission it, you should have it tested thoroughly. So this is an example of a calculation. Again, this is my equation over here. Radiation heating load Q, this is from the book. Radiation rate, the area of the panel in square foot for each panel. The panel here being the floor, or it could be a wall as well. So again, this is a manipulation of the equation. I know it looks a little bit unorganized, but if you look at the end of the book, it looks much better. So the DT is the water temperature and the room temperature, and the DT calculation can be calculated. If we go back to the other equation, if you want to solve for the DT, it's going to be Q over RR times area. And if the DT is the temperature of the water minus temperature of the room, so eventually if you want to calculate what temperature of the water is required to increase the temperature of the room, this is the equation you're going to solve for. And this here is the equation that you can use for calculating the area. All these are just based on one equation, and I just manipulated it to solve for something different. So if you look at that in the book in page 159, you'll see these equations in here. Okay, so let's look at this example. A room that has a heat loss of 8,000 BTU hour is 20 by 30 feet, is to be kept at 75. The water temperature is 85. What is the required radiation rate? So this is the equation as is, and we try to solve for the radiation rate. Now we find the area, then DT is 10. Finally, we solve for the radiation rate. So we need something that gives us this radiation rate over here. I don't know what this is. doing it for some reason. But anyways, so this is the radiation rate required, which is 1.33 BTU per square foot for that floor, which is very modest radiation rate. In this example, we are solving for the water temperature. Let's say we want to keep the room at 75. We have a limited, we have a heat loss of that room is 400,000 BTU, and I mean 4,000 BTUs, and we have a limited radiation rate. Let's say this is what the company is saying, radiation rate of 10. I can control the water temperature. So in this way, I will solve for the water temperature. So this is TW is the temperature of the water, and TR is the temperature of the room. And I found out that I have to put the water temperature at 75 degrees. And again, you probably will have a water heater that keep the water at 85 or 90, and you can dispense water at any temperature you want using thermostatic valves. Okay, radiation rate, Q, and this is the water temperature. It's going to be at 80 in here. So look over these examples, and they are also in the book. So if you want to know how these equations are used and how do you calculate each one of those aspects. The last example here that we have is a room that has a heat loss of 2,000 BTU hour. Probably it's a bathroom. It's kept at 65, and the radiation rate is 5 BTU per hour. The water temperature is 85. What is the panel area required, be it the floor or a wall? So again, it's the water temperature. This is the radiation rate, and this is the heat loss. The area is equal. From the book, you can find here that this equation is available over here. To look at the area, probably it's somewhere in here, and area equal Q over RR times DT. We find the area. So this is the area required to have 20 feet of panel. So you have to decide what you will need for this area. So 20 feet can be divided in so many ways. So it's going to be 5 by 4. So it's not that big of a panel to heat that space. So if it's a bathroom, you don't need to heat the entire floor, only a small portion of the floor that is exposed to the air. Okay, so I'll stop now and continue in the next video, where you will find some how to select the boiler location based on the NFPA requirement. Thank you.